Here is an example numerical problem related to reaction turbine. This is example 11.4 from the book of McConkey. A stage of steam turbine with Parsons blading delivers dry saturated steam at 2.7 bar from the fixed blades at 90 meter per second. The mean blade height is 40 millimeter and the moving blade exit angle is 20 degree. The axial velocity of the steam is 3/4 of the blade velocity at the mean radius. Steam is supplied to the stage at the rate of 9,000 kg per hour. The effect of blade tip thickness on the annulus area can be neglected. Calculate, number 1, the rotational speed of the wheel. Number 2, the diagram power. And number 3, the diagram efficiency. And number 4, the enthalpy drop of the steam in this stage. So, the data of this problem, we are given that it's a turbine with Parsons blading, which means it is 50% impulse and 50% reaction. That is, degree of reaction is half. The velocity diagram must be symmetrical. State of fluid after fixed blades is given. The fluid is dry saturated at the inlet to the moving blades at a pressure of 2.7 bar. So we can determine the specific volume at this pressure from the steam table. Specific volume will be the Vg at 2.7 bar. So this is 0.6686 cubic meter per kilogram. The absolute velocity at inlet is 90 meter per second. Mean blade height is 40 millimeters. The moving blade exit angle beta E is 20 degree. From symmetry, this will be equal to alpha I. The velocity of flow is 3/4 of the blade velocity. The mass flow rate of steam is 9,000 kg per hour, which should be equal to 2.5 kg per second. This is all the data given in this problem. And we have to determine these 4 things. 1, we have to determine the speed of the moving blade wheel. We have to determine the diagram work, the diagram efficiency, and the enthalpy drop in the stage of the reaction turbine. So here is the velocity diagram. The upper side is CB, the blade velocity. On the right side, we have the inlet velocity triangle. The larger side being the absolute velocity CAI, which is 90 meter per second. The value is given. The smaller side here will be CRI, the relative velocity at inlet. And the vertical component of the absolute velocity will be CF, velocity of flow. So the angle of the absolute velocity is, or the nozzle angle is 20 degree. We are given, here we can determine the velocity of flow from this formula. CF will be CAI sine alpha I. So this will be 90 into sine 20 degree. We obtain 30.78 meter per second. Next, we can determine the blade velocity since we know the ratio of blade velocity and the flow velocity. So since CF is 3/4 of CB, CB will be 4/3 of CF. 1.33 into 30.78, we obtain 40.01 meter per second for the blade velocity. First part asks us to determine the rotational speed of the blade wheel. We have this formula relating the blade velocity with the rotational speed. We have just determined the blade velocity. We know the value of, we need to determine the value of rotational speed. The only unknown before we determine N is R. So we first need to determine the value of R. R is the average radius of the blade wheels. As we know that in a turbine, the moving blades are mounted on the periphery of a wheel. The middle section of the wheel is closed for the fluid. Fluid cannot pass this section. Only through the annulus where the blades are mounted, the fluid can pass. We call the available area for the fluid to pass as area A, the area of the annulus, and the blade height is H. We can calculate the annulus area from the formula of mass flow rate. It should be equal to m dot is equal to A into Cf over small v. A is the annulus area, Cf the flow velocity, that is the velocity perpendicular to the annulus area. And V is the specific volume. So A will be equal to m dot V over Cf. M dot is 2.5, V is 0.6686, and Cf is 30.78. The annulus area is equal to 0.054 square meters. Next, we can obtain the value of radius by writing a formula for the annulus area in terms of radius. So area is equal to 2 pi RH. So R is area divided by 2 pi H. We substitute values. The radius becomes equal to 0.215 meter. Okay, now we have determined the radius. We can substitute the value of radius here to determine the value of rotational speed. So N is equal to CB divided by 2 pi R into 60. We substitute values 41.04 divided by 120 pi into 0.215. Notice since we are writing a value of 60 here, we are taking the value of N in RPM. So with this formula, the value of N will be in units of RPM, revolutions per minute. After calculation, we obtain 1824 revolutions per minute. Or if we want to convert into RPS, 30.4 RPS is the answer. Next, we calculate the diagram power. Formula for diagram power is W dot is M dot CB delta CW, where delta CW can be calculated by this formula, 2 CAI cos alpha I minus CB. Notice that this formula is only applicable for the Parsons type of reaction turbine. So we substitute values and delta CW comes 128.1 meter per second. So the W dot would then be M dot 2.5 into CB 41.04 into delta CW 128.1. We obtain 13,143 watt or 13.14 kilowatt. Next, we need to determine the diagram efficiency. So first, we need to determine the diagram power per unit mass flow rate CB delta CW. This is 5257 kilojoule per kilogram. And the energy input per unit mass flow rate is CI square minus CRI square by 2, where CRI square can be determined by this formula. CRI square is equal to CAI square plus CB square minus 2 CAI CB cos alpha I. So after solving, we will obtain CRI equal to 53.32 meter per second. If we substitute this value in the formula for energy input, we obtain 6679 joule per kilogram. So the units of En is in joule per kilogram. The units of energy input per unit mass, the units of diagram power per unit mass flow rate written here, they are also in joule, not kilojoule. So you can make this correction. Finally, the diagram efficiency will be diagram power divided by the energy input, 5257 over 6679, 78.7%. 78.7%. last portion, enthalpy drop in the stage H2, H0 minus H2. This should be equal to twice of the enthalpy drop in the moving blades row, H1 minus H2. So we can first determine H1 minus H2, and then we can multiply by 2 to determine the enthalpy drop in the stage. So enthalpy drop in the moving blade will be determined by this formula, H1 minus H2 is equal to CRE square minus CRI square divided by 2. Substitute the values, since from the symmetry of the triangle, CRE is equal to CAI, which is 90 meter per second. And CRI we determined 53.32. So you can substitute the values, calculate. The answer is 2.63 kilojoule per kilogram. Therefore, enthalpy drop per stage will be twice of this value, that is 5.26 kilojoule per kilogram is the final answer. This completes the problem. Here are two numerical problems for you to try to solve on your own as homework problems. This is first exercise problem 11.7 from the book, and this is another 11.8 from the book. Thank you.